Welcome to the Problemers channel, season 3, episode 39, the episode which I titled "A Massive Bead Sliding Without Friction Off of a Absolutely Rigid Massless Rod that Rotates with a Decreasing Angular Velocity," in which we will solve a sister problem of the original physics problem S2P2, whose solution we looked at in great detail in season 2, episode 54. But before we deep dive into the underlying physics of the variation of this problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled "The Problemers Channel How To." We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode of interest on this channel and use the comment section under that episode. And because lately I've been asked the question of how do I use this channel on a regular basis, in addition to the video material that I just described for you, I put together a written document called "How To," and the link to that document is in the comment section of this episode. The physics problem S3P9 is a sister problem of the physics problem S2P2, whose solution we looked at in great detail in season 2, episode 54. If you missed that episode, you may want to refresh it in your memory. The link to that episode is in the comment section to this episode. But in that original problem S2P2, we were given an absolutely rigid massless rod, shown in blue over here on the left side of your screen, of length L, that rotates in the horizontal plane with a constant angular velocity omega 0 with respect to a fixed vertical axis of rotation. In the initial steady state, on that massless rod there sits a bead, a point mass M, shown in red, and that bead is fixed on the rod with at the distance of L0 from the fixed vertical axis of rotation, let's say with a thread. At some point of time, the thread that holds the bead or the point mass in place at the distance L0 from the fixed vertical axis of rotation is cut, and the bead begins sliding without friction along the rotating rod towards its free edge. And the objective of that problem S2P2 was to find the separation velocity of the bead with respect to the rotating rod and the separation time. Now we know that experimentally, in mechanical part of physics, if you will, we know about 3 quantities that are conserved in certain situations: energy, linear momentum, and angular momentum. The angular momentum of this system in the initial state, because the rod, remember, it's absolutely rigid and it's massless. Of course, we should understand that this is just an abstraction. That simply means that the mass of the bead M is way, 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 way larger than the mass of the rod L. But in this case, the angular momentum of the system will be M, the mass of the bead, times the square of the distance L0 from the fixed vertical axis of rotation, times omega 0. And according to the law of conservation of angular momentum, in certain cases when it holds, that angular momentum should be equal to the mass times x squared times omega, where x, again remember, is the distance of the point mass from the fixed vertical axis of rotation along the rod L. If we place the origin of our implied reference frame into the point where the fixed edge of the rod comes into the contact with the vertical axis of rotation, and that distance will be measured as x. So since mass of the bead is constant, this distance is constant, this quantity is constant, the angular velocity with which the system rotates in the horizontal plane. Again, on the right-hand side, we have constant mass. So the coordinate x grows, and if that coordinate grows, for this quantity to remain constant, it means that the angular velocity must decrease in a certain way. But we're told that in this particular case, in the original problem S2P2, that law of conservation of angular momentum did not hold, because despite that fact, and I hope that many of our viewers have seen this experiment in action with the, for example, with the figure skater, when the figure skater spins quite fast in place, holding the hands to the chest at a high rate of rotation, and then when the skater moves the hands apart, then according to the law of conservation of angular momentum, in this case it is applicable, the angular velocity of this figure skater slows down. In other words, the figure skater begins rotating slower. And in this particular case, we were told that despite that fact, the whole system, massive bead and the massless rod, they still rotates at the same constant angular velocity omega 0. That was the problem statement for the problem S2P2. And what does that mean? That means that there was a carefully calibrated input into the system. Let's say somehow the fixed vertical axis of rotation was supplied input into in such a way that it still maintained the same angular velocity as the bead moved away from the axis of rotation. You know that the further the mass is away from the axis of rotation, the more effort it needs to be applied to that point in order to rotate it at the same angular velocity. So we solved that problem in season 2 episode 54 in all details, but back then we noticed that we have a choice at this point. We either take it that the whole system rotates at the constant angular velocity omega 0 anyway, and this is what we did. But back then in season 2 episode 54, we also mentioned the fact that what will happen if there is no external input into the system, and once the thread that holds the point mass in place at a distance L0 from the fixed vertical axis of rotation is cut, and the bead begins sliding without friction away from the axis of rotation towards the free extremity of the rod, there is no input. What does that mean? Well, that means that the law of conservation of angular momentum, whose symbolic representation you just saw, holds, and that means that as the distance x of the point mass from the fixed axis of rotation, or from, let's say, origin of our coordinate system, which we place this way, this how the x will run, increases. That means that the angular velocity of the system bead rod does what? Decreases. So this is exactly the case as in this problem in season 3, physics problem P9. The angular velocity decreases over time, but we still want to answer essentially the same questions. We want to find the separation velocity of the bead relative to the rod when the point mass m reaches this free extremity and jumps off. What was the velocity of this point with respect to the rod? And we also want to know how much time, how long did it take, how many units of time did it take for the point mass m to reach the free extremity of the rotating rod. And obviously an interesting question in this case, we want to recover the shape of the function that explains the behavior of the angular velocity omega, the decreasing angular velocity omega with time. I will solve this problem using the machinery of the Lagrangian mechanics. You can use any other machinery that you like, but to that end, we will place the coordinate system in our problem in such a way that the vertical axis y coincides with the fixed horizontal axis of rotation this way. This will be the y-axis. The x-axis will coincide with the rod, so the position of the point mass m on the rod at any time can be described completely with just one real number to which we will refer as x. That means that our system possesses only 1 degree of freedom, and in this case we will also choose the x-axis over here, or the level at which the rod is rotating in the horizontal plane, to be the level when the potential energy U is equal to 0. And in this case there is no friction, the law of conservation of energy holds, and the kinetic, or let's say the Lagrangian L, will be the difference between the kinetic energy T minus the potential energy U, which is set to 0 at this point. And since the rotation always happens at the same level, we will have the potential energy of our system 0. So this will be only the kinetic energy, and the kinetic energy of our system comprised of what parts? Well, we have a rod because we take the rod to be massless. It possesses no kinetic energy, no angular momentum. So the only kinetic energy in the system will be supplied by the rotating bead that also moves along the bead, and the motion of that point at any time. Let's say the bead is located over here, then the distance of the bead from the fixed vertical axis of rotation will be x. So at this point, let's say at this point, what will be the kinetic energy of the bead? Well, it will be the moment of inertia. Let's say we will designate it like this: omega 0 times omega squared over 2 plus the kinetic energy that is associated with the linear or the translational motion of the bead along the rod. And that will be what? Mx dot squared over 2. So here, let's say we will agree that in this case x dot will be the good old linear velocity v of the bead with respect to the rod. Now the moment of inertia of a point mass is as pleasant gets. It will be mx squared times omega squared over 2 plus mx dot squared over 2. This will be the Lagrangian of our system, and now all we have to do is recall that in this case we will have the following relations that will hold: the first time derivative of the partial derivative of the Lagrangian with respect to the generalized velocity, which in this case in some sense is traditional velocity, must be equal to the first partial derivative of the Lagrangian with respect to the generalized coordinate, or in this case this is our traditional coordinate x. So now, since we have our Lagrangian, the shape of the Lagrangian is known. This is shown on the upper right hand side of your screen. Let us carry out these straightforward computations. Let us do this guy first. So this will be the first partial derivative of this expression with respect to coordinate x. Remember that in this case all the other material is taken to be fixed. So since this is the only variable, the first derivative of x squared will be 2x. 2 and 2 cancel out, so we'll have mx omega squared. This is this portion of the Euler-Lagrange equations. Now let's compute the first partial derivative of the Lagrangian with respect to the velocity x dot. It will be what? Look at this. All the other material, everything else in this Lagrangian is taken to be constant when we carry out this partial differentiation. So the first derivative of x dot squared will be 2x dot. 2 and 2 cancel out, so we have mx dot. And now we take what? Now we take the first time derivative of this expression. So the first time derivative of this expression will be what? It will be technically m dot x dot plus m x dot dot. With dots I will designate traditional time derivative in physics, but the point mass remains what it is during the entire experiment. The mass does not change, so this term in this case vanishes, and we only have left with what? We're left with mx dot dot as our left side of the Euler-Lagrange equations. And if we equate the two, then we will have what? We will have mx dot dot is equal to mx omega squared. We divide this equation through by non-zero mass. Mass is not equal to zero. Cancel out on both sides. And what do we have? We have our differential equation of motion x dot dot equal to omega squared times x. Do realize that now we have an ordinary differential equation of order 2. This equation is linear because the derivative of interest over here enters into this equation in the first power. But we need to realize that now we have two functions. The second derivative of the coordinate of the moving bead along the rod is equal to the product of two varying quantities, of two functions that vary over time. We know that the angular velocity of the system varies over time, and the coordinate varies over time. In other words, we have omega as certain function of time, and we have coordinate as a certain function of time. And now we will work with this equation in order to answer the first question of what is the separation velocity of the bead when it reaches the end of the rotating rod. Now, at the beginning of this episode, you saw the thumbnail, which contained the following mysterious letters in the circle: L, M in the circle. Evidently, this stands for Lagrangian mechanics. And as a short quiz, what do you think this will stand for? NM. NM will stand for, evidently, Newtonian mechanics. And if you will see HM, then it will be what? Hamiltonian mechanics. If you will see K in the circle, then it will be what? Kinematics. And so on. You understand the idea. I think that if I will put this information into the thumbnail, then it will make your life much easier, because at a glance you will be able to see what machinery this particular physics problem is cracked by, and you can then decide for yourself, before even spending any time on figuring out what's going on in this episode. Save some time for you, and at a glance you will see what is going on. Now here we have our linear ordinary differential equation, in which the second time derivative of the coordinate x of the sliding without friction bead m is in the first power. It is linear, but now this ordinary differential equation also happens to be in separable variables. In other words, it is possible to separate the variables in this equation, and moreover, amazingly enough, it is possible to solve this equation analytically, or in a closed form, the so-called closed form, or as a finite combination of elementary functions. This is basically a miracle. At first, when you begin solving these problems, then they seem to be difficult, because as much as you can read all sorts of books on theoretical physics, or you can sit through many lectures and listen to the theoretical part of theoretical physics, you will never understand how these things work until you begin actually solving problems yourself. Every step of the way, every millimeter, every step and every blow must be carried out by you. And initially these problems will be difficult, the differential equations will be scary, but then as time goes by, what seems to be difficult will become not so difficult, and then even some more time later, this will become a baby problem, and you will take on the differential equations that actually cannot be solved analytically, and the whole layers of mathematics are developed around the ability to tell something about the solution, not to spell out the solution explicitly, but generate information about the solution. In any case, here we step as follows. What we're about to do is called in theoretical physics and in mathematics is called the reduction of the order of the differential equation. In other words, instead of dealing with the differential equation of order 2, we want to bring that order down and try to pick the fight and win that fight with the differential equation of order 1. How do we do it? Well, we spell out the definition of the acceleration, the second time derivative, which is what? The first time derivative of the first time derivative. What is the first time derivative? The velocity. So look at this. From here we have x dot dot is equal to the first time derivative of x dot, right? So this is equal to dv over dt. Now what do? Well, we multiply this by 1 and without changing the value, dv over dt times dx over dx, and then we bring out the right hand side, omega squared x. And now what do? Now look at this. Let me grab some other chalk, some other color. Look at this. We carve out this. Look at this. See, what is this? dx over dt. dx over dt. Well, this is our favorite usual suspect, v, the velocity. So from here it follows what? We have the following string of symbolic manipulations. V times dv, v times dv is equal to dx in the denominator. The first differential of x can be swung to the right hand side of this equation, so we will have omega squared times x times dx. And now the idea, of course, over here is we try to find the separation velocity of the bead when it reaches the free extremity of the rotating rod. What is the end goal of all these manipulations that we're doing? Well, the end goal of all these manipulations is to construct a function v as a function of x, as a function of x, because then how can we solve, how can we answer the first question? Well, if x is equal to L, then v becomes our separation velocity, the separation. So we can spell out explicitly the function of x for velocity. When we replace x with L, then we will be able to do what? And we will be able to recover, in other words, let's call it arc v, arc phi. Then it will be ov, will be x, and if we put L over here, we can also recover the value of the separation velocity. So now what do? We recall keep this in mind. Let's over here write the law of conservation of mechanical energy in our case. So it will be the moment of inertia and then times angular velocity, the constant angular velocity omega 0 over 2 initially, because our bead, remember, it is fixed to the rod in some sense with, let's say, with the thread at the distance L0 from the fixed vertical axis of rotation. This is the only component that generates kinetic energy for our massive bead. And then once the bead is in motion, once the thread has been cut and the bead begins sliding along this rotating rod without friction, then its moment of inertia will change. Then its angular velocity will also change over 2 plus mx dot squared over 2. This is the law of conservation of mechanical energy. What do we see? 2's cancel out. And then in this case, what do we have? We have ml squared 0 omega squared 0 is equal to mx squared omega squared plus mx dot squared. What do we see? Well, in this case, non-zero mass cancel, cancel, cancel all over the place. So now we can isolate this usual suspect and write down the following. Omega squared x squared times omega squared is equal to L squared 0 omega 0 squared minus x dot squared. You see, once we divide this result through by x, then what do we have? Let's see. Let's write it down. Omega squared will be equal to L0 squared times omega 0 squared minus x dot squared divided by x squared. Write down this result. I will not be numbering it, but you should number it any which way you like, because we will come back to this equation a couple times as the solution of our problem unfolds. But now we take the square from this expression and we inject it over here. What will we have in this case? Well, it follows then we will have v times dv is equal to, let's write it down like so, L0 squared times omega 0 squared minus x dot squared divided by x squared. You see, we put this over here, and then we have times x times dx. You follow so far? X cancels, one copy cancels, and what do we have? We have over here L0 squared times omega 0 squared minus x dot squared divided by x times dx. You see, v times dv is equal to this. Now, x dot squared is what? Remember our designation over here. So now we can separate the variables. Look at this. All the material in our differential equation that relates to v goes on the left-hand side, and all the material in our differential equation that relates to x goes onto the other side of the equal sign. So once we do that, what will we have? Look at this. The numerator on the right-hand side of the equal sign goes into the denominator of the left-hand side. So we will have v times dv divided by L0 squared times omega 0 squared minus v squared. You see, v squared, I just replaced x dot with v. It's easier on the eye. We could have operated in terms of x dot all the time, but then this is just more natural, more organic way to work with these things. Plus, it tells you that what we're doing in this case, as I told you before, we're reducing the order of the differential equation that we're working with. So this is equal to dx over x. You see, this is how straightforward these things are. What do we do now? Now we integrate, and in this case, in general, we carry out the integration in the indefinite sense. We aggregate or absorb all the constants into one on either side of the equal sign, and then we recover the value of this constant of integration using the initial conditions. What are the initial conditions in our case? Well, look at this. Let me write it down over here for you so that you remember. The coordinate x at the time t, let's say 0, is equal to L0. This is more than straightforward. This is captured over here. And because the system in steady initial state rotates in such a way that the thread is tied to the fixed vertical axis of rotation, that means what? That the velocity of the bead with respect to the rod at time 0 is what? 0. Exactly. There's no initial velocity of the bead with respect to the rod. So we integrate. On the left-hand side, we integrate from where to where? From 0 to the current value of v. And on the right-hand side, we integrate from where? From L0 to what? To the current value, x. The integral on the right-hand side is trivial. It is simply log of absolute value of x taken between L0 and x. This is trivial using the basic property of the logarithmic function. This will be logarithm of x divided by L 0. Look at this. This is the first part we've done over here. And now let's say you see what happens over here. Keep this in mind, but let's unfold this integration over here. We'll erase it. Now, what do you see on the left-hand side of our integral relation? This one, look at this. V isn't squared in the denominator, but here we have the expression v times dv. That means that when we move v under the differential, we generate the v square. We take it with the minus sign, and we take 1/2. So we will say 1/2 of the integral that looks as follows: d L0 squared times omega 0 squared minus v squared divided by L0 squared times omega 0 squared minus v squared. You see how straightforward that is? So we have essentially the integral over here that looks as follows: d f of something divided by f. This is what? Natural logarithm. So this will be again minus 1/2 logarithm of, let's take it this way, L0 squared times omega 0 squared minus v squared, taken between the boundaries of what? 0 and v. And I will put it like this. Now, when v at the lower boundary is 0, then this summand disappears, only this one remains, and this is taken with the minus sign, this becomes the plus sign. So let me erase this material over here. These integrals, eventually you will come to appreciate these integrals because they're baby integrals. So now we have, so let's write down this way. It goes this way. So now we have 1/2 of the logarithm of L square 0 omega square 0, like this, minus 1/2 of the logarithm absolute value. Here at the upper boundary of integration v, we get our v, so we have the logarithm of absolute value L0 squared times omega squared 0 minus v squared absolute value. Now, once we take 1/2 out, look at this. Here we have the product of two squares, so this can be squared, can be aggregated, carried out in front of log. So this will be, so this will cancel the 1/2, and then 1/2 for this guy can be carried into with the square root. So what is this? Well, this will be the logarithm of absolute value of the following: L0 omega 0 divided by square root of L0 squared times omega 0 squared minus v squared absolute value. And this logarithm, remember, must be equal to this logarithm right here. So let me now erase some more material over here, make room, and then we will continue. And unlike its complex counterpart, the single variable real-to-real logarithm over here is a continuous and traditional single-valued function that is also monotonically increasing. Let's say this is z, strictly real. This is log of z. So let's say this is 1, this is 0, right angle, this is also 1. So the graph, the partial graph of the logarithm will look as follows. Let's say I'll use yellow. It will come out from negative infinity and slowly come up to positive infinity, very, very slowly. But the fact that this function monotonically increasing means that if we have a strictly less than b, then it means that the logarithms, log of a will be strictly less than log of b over here. This will be the delta between them. But if it so happens that the values of the logarithms match, it means that their arguments must match. There is no choice. In the over the field of complex numbers, this is not the case. The logarithm is a multi-valued function, but luckily for us here, we're not dealing with complex numbers and not the field of complex numbers. We're working over the set of real numbers. So if two logarithms match, that means that their arguments match, and that means that we have L0 times omega 0 divided by the square root of L0 squared times omega 0 squared minus V squared must be equal to what? It must be equal to x divided by L0. This is a simple consequence of the fact of the properties of the logarithmic function. Real to real, single variable, continuous, single valued, monotonically increasing. So from here, let's say we cross multiply. What do we have? We have L0 squared. L goes to over here from the denominator on the right hand side and the numerator of the left hand side. So is the square. L0 squared times omega 0 is equal to, what is equal to x times square root L0 squared times omega 0 squared minus V squared. And all we have to do now is isolate V in this case and solve this equation for V in terms of x, construct a function of V in terms of x. So here, look at this. From this, if we square both sides, then what will we have? We'll have L0 to the fourth times omega 0 squared is equal to x squared times L0 times L0 squared. Let's say we'll take it that way. L0 squared times omega 0 squared minus x squared times V squared. So we move this guy, let's say, to the left hand side. We move this suspect to the right hand side. So from here, what do we have? X squared times V squared is equal to x squared times L squared 0 times omega 0 squared minus L to the fourth 0 times omega 0 squared. This is what we have. Now, if we divide this equation through by x squared, by the usual suspect x squared, divide through, what will we have? We will have, for the square of V, we will have L squared L0 squared times omega 0 squared minus, over here, remember I forgot it was a small typo, and minus, what is it, L0 to the fourth power omega 0 squared divided by x squared. Now look at this, L0 squared omega 0 squared, these two factors can be taken out, so we will have L0 squared times omega 0 squared 1 minus, look at this, we had the fourth power, we took out the second, so we will have L0 squared divided by x squared. Now what do we do? Since this is V squared, we take the square roots of both sides again. Square root of a real argument is single valued, continuous, monotonically increasing, and so on and so on. So now we take square root of both sides. We will have V is equal to plus minus L0 times omega 0 times square root of 1 minus L0 squared of x squared. And between two signs, plus and minus, which one do we take? Well, in our case, as x grows and as time flows forward, our velocity has to increase, stay positive. So we take the plus sign. So this is our, look at this, this is our result. V as a function, V as a function of x. Now simply we put, instead of x, remember our discussion x we replace with L. When the coordinate x becomes L, this number right here, that means that the bead reached the free extremity of the rotating absolutely rigid massless rod, and that constitutes the event of separation of the bead from the rod, and that part of the problem is solved. So we can write down the result. Let's say we write it over here. The separation velocity, V separation, will be, what will be, L0 times omega 0 times square root of 1 minus L0 squared divided by L squared. And look at this. As a hard scientist, you should always be skeptical, no matter what, no matter when, no matter what the circumstances. If you meet any person who calls him or herself a hard scientist and you realize that this person is not always skeptical, that person is a fake hard scientist. So here we're always skeptical, even though we're pretty sure that we did things right. But look at this. So we have, by condition, L0 is less than L. That means that L0 divided by L is strictly less than 1. The square of a quantity that is less than 1 is even smaller than 1. So from 1 we're subtracting a quantity that is smaller than 1. So this number over here under the square root will be strictly positive. And it is okay to take a square root of a positive number, and over the field of real numbers, that is the only square roots that we're allowed to extract, non-negative. We cannot extract a square root from a negative quantity over the field of real numbers. It can be done over the field of complex numbers, but not over the field of real numbers. But in our case, everything seems to be mathematically, everything seems to be in a good shape, and we have our answer. And there is one interesting phenomenon over here. Let's do this. Let's compute the limit when x grows without bound of our velocity v of x. This becomes the limit of x tends to positive infinity of the following quantity: L0 omega 0 square root of 1 minus L square 0 over x square. What is the value of this limit? The value of this limit is evidently when x grows without bound. 1 over a very large number tends to 0. 1 minus 0 is 0. Square root of 1 is 1. And we have our answer. L0 times omega 0. And that answer can be interpreted as follows. Left to its own devices for a sufficiently long time, if, of course, we have another, at this point, even more mathematical abstraction where we have, instead of a rod of a finite length L, which is always the case with everything physical, here we now switch to kinematics pretty much, and we have the ray rotating in the horizontal plane with the angular velocity whose shape we will discover right now as a function of time. We know that as a function of x coordinate and velocity, this shape is right here, but we will unwind these functions as the functions of time. But given enough sufficiently long amount of time, if the bead runs far enough under this condition, then its velocity, look at this, its velocity stabilizes, asymptotically approaches this product, and dimension-wise everything squares, because this is units of distance, this is reciprocal units of time, 1 over time. So distance over time gives us precisely the velocity. Everything makes sense. So if you graph this function, it will mathematically contain two branches. It will look as follows. It will consist of two branches. Let me do it this way. It will run like this, and it will run like this. But this value, the horizontal asymptote right here, will be exactly what? What is this? Well, this is the number. And we will come back to that number when we uncover the shape of the function v of t, of time t. But then we will compute the similar limit when time grows without bound. And now that we answered the question of what is the separation velocity, here it is. Now we will answer the following question. What is the separation time? In other words, how long did it take the point mass to slide from the point where it was sitting in the steady initial state all the way to the end of the rod. To that end, our battle plan is the following. Construct a function x equal to, let's say, f of t. And then if we succeed at constructing a function that is given explicitly or in the so-called closed form as a finite combination of elementary functions, then taking the inverse of this function when x is equal to L, then it follows that the time that we will recover through this operation will be the separation time sought after. And in this case, we will do what? We will say, let's say, arc f. So this will be the inverse instead of writing this horrible -1 notation. Basically, the inverse of f from here will give us the separation time. This is it. That's the battle plan. That's the overall big picture. We keep it in mind. And usually in most textbooks that you will see, this will never be said, but this will always be implied. Now, what do we do over here? Well, look at this. We have our 3 results that we developed gradually. You saw how we developed this step by step. All the deductions were transparent. The differential equation of motion, single 1 degree of freedom, Euler-Lagrange equations. I put this guy over here. We deduced this from the law of conservation of mechanical energy initially and at any point in time when the bead was sliding along the rod. And we deduce this by solving the corresponding differential equation by replacing omega. Here we recovered the function of x for the value of v, the velocity of the bead relative to the rod. So now we do the same thing. Basically, we take this v squared, which I remember we had this expression over here as a square root, but here we take the square. This is the expression. We take this square, we put it over here for omega squared. So we have omega squared will be equal to what? Look at this, L0 squared, omega 0 squared minus this term cancel out. This minus times this minus becomes a plus. So we will have the following expression, L0 to the 4th times omega 0 squared times 1 over x raised to which power? 2 plus 2 is 4. Raised to the 4th power. So now we take this omega and we insert it into our original differential equation. What we will have then? Well, in this case, we will have the following result. Again, the second time derivative, xx, is equal to, let's say, the constant k. We'll designate it as a k. Here we have 1 copy of x in the numerator. We have 4 copies of x in the denominator. What's the result? The result will be k divided by x cubed. And this is basically a symbolic sugar. Here we will say k equal to this guy right here. This is k. L0 to the 4th times omega squared 0. So that we do not write all this horrible jumble of symbols all the time. So now we have another wonderful ordinary differential equation of order 2. This equation is also with separable variables, and it can be solved completely in closed form, analytically, if you will. And the way we solve this equation is pretty much the same way we solved the equation when we dealt with the velocity. So here we will write x, the second time derivative of x is the first time derivative of the first time derivative, dx dot. So here we will write it like this. We'll multiply it by 1, multiply it by dx, and divide it by dx. So this, again, you already know the maneuver. I will not spend much time. This will be x dot times dx dot divided by dx, and this is equal to k over x cubed. So now we move the differential dx from the denominator of the left-hand side to the numerator of the right-hand side, dx like so. And then what do? Well, we integrate both sides, integrate, and then for now we will keep it in the indefinite form. From here it follows what? From here it follows that x dot squared over 2 is equal to what? Remember that if, let's say, mu is any real number such that it's not -1, then the indefinite integral x raised to the power mu dx is equal to x mu plus 1 over mu plus 1. And in this case, mu is equal to what? -3. So -3 plus 1 becomes -2. -3 plus 1 becomes -2. This result is your high school integral calculus. You remember this very well. So what do we have here? We'll have minus k over 2x squared plus some constant of integration. How do we recover the constant of integration? Well, we go back to our initial conditions. We know that initially the velocity of the bead was 0 and its initial displacement from the fixed vertical axis of rotation of our absolutely rigid massless rod was what? L0. So we have it at the moment of time t equals 0, x dot is 0, big fat 0. What is x at the moment of time t equals 0? It is L0 to L squared 0 plus c. So what is the constant? We have the minus sign over here, 0. So what do we have for c? Let's erase it like this, write it this way. So what do we have? c is equal to k over 2L0 squared. So now, since we recovered this expression, we can write it as follows. X dot squared over 2 is equal to k over 2L0 squared minus k over 2x squared. So far so good, so far so good. Now we cancel out the 2's, and then we multiply this horrible thing through by what? By the product L0 squared times x squared to clear the denominators over here. What will we have? We will have on the left hand side L0 times x squared times x dot squared is equal to, here what will survive? L0 squared will cancel out. We'll have k times x squared minus, here on this side x squared will cancel, but this guy will survive. So k L0 squared. This is our result so far. Look at this. This is the intermediate result. Make sure you understand where it came from. And what do we do now? Well, now we want to prepare this. Result for another separation of variables, and the way we do it will be as follows. Again, we take the square roots of both sides of this equation, and since we have squares all over, I forgot the square over here, we will have the product of L0x and x dot on the left hand side. On the right hand side, technically we need to take plus minus square root of this here expression, but now let's think about which sign do we pick. As x grows, look at this, as the coordinate x of the sliding bead m grows when the time flows forward, its velocity is also increasing. So the product of two positive quantities, which means that if x grows and the velocity grows, it means the derivative, the first time derivative, x dot, must be positive, and the product of two positive quantities is a positive quantity. And when the time flows in reverse order, as x decreases, x dot velocity decreases, and then we have the product of two negative quantities, again a positive quantity. So once we take the square root of the left hand side and the right hand side, on the right hand side we will keep which sign? The plus sign. So from here it follows what we will have: L0 times x dot is equal to, I will write explicitly, plus square root of kx squared minus k L0 squared. And now we, as I promised a few seconds ago, we separate the variables one more time. We spell this x dot as what? We'll spell it as dx over dt. You see, this is how the separation of variables works. And now we grab all the material that contains or deals with one variable, we move it to one side of the equal sign. And all the material that deals with the other variable, we slide it onto the other side of the equal sign. So on the left-hand side of the equal sign, what's the material that deals with x? Well, we have L0 times x times dx divided by square root of, let's say, let's not deal with k. We will factor it out, square root of k, so we don't have to deal with it. So it's x squared minus L0 squared. We'll keep it nice like that. And then what do we have? The first time differential dt flows to the right-hand side, but then we'll have the square root of k times dt. You see, it goes like this. This is our result. We factor out square root of k here and here, take it out so we don't have to mess with it over here on the left-hand side. And look at this. You already see what's going on. X dx. We'll move x under the differential with the plus sign minus the constant makes no difference. So you already see how these things will work out. Let me erase this material over here. You now can rewind if you have to, but we will make room for it over here. And let's do this. We will integrate the left-hand side from where? From L0 to x. And we will integrate the right-hand side from 0 to t, current time. Initial time is 0, current time t. Initial coordinate, because we're carrying out the integration over the coordinate x, L0, and the current one, x. So what do we have here? Well, here we have a trivial result, square root of k times t. You see? This is as straightforward as it gets. And what do we have here? Well, let's write it down like so. Let's write it down. This integral right here, I'll carefully mark it, slug it in over here. So what do we have here? We have 1/2 of L0 integral d of x squared minus L0 squared over square root of x squared minus L0 squared. And what do we have? D, something over square root of that something. Game over. So here we will have the following result. Minus 1/2 plus 1 is plus 1/2, positive 1/2. In the denominator, this fraction will flip into the numerator, so 2 and 2 will cancel out, and we'll have the following result. L0 square root of x squared minus L0 squared, evaluated between which boundaries? Between the boundaries of L0 and x, the current value. When x is equal to L0 squared minus L0 squared evaporates, and what do we have left over? Only the value of this function at the upper boundary. So this will be L0 times square root of x squared minus L0 squared. Isn't that wonderful? And this whole mess must be equal to the square root of k times t. This is square root of k times t. What is your next maneuver? Your next maneuver, because we want to extract the expression, the closed form or analytic, if you will, expression for the function x as its argument t, we need to isolate x. So we will have the following result. L squared 0, we square both sides of this equality. We have L0 squared times x squared minus L0 to the 4th. That is equal to what? Square root of k. Remember, we had k equal to L0 to the 4th times omega 0 squared. That was our k. So we have k times t squared. And now instead of k, we put this expression over here, L0 to the 4th, omega 0 squared times t squared. Don't forget that the time over here is in the second power. So now what else can we do? Look at this. L squared cancel out. This L4 becomes L2. This L4 becomes L squared. So we have the following result. X squared is equal to L0 squared plus L0 squared omega squared 0 t squared. What can we do over here? Obviously, L squared can be factored out. Once we take X, we will have again X will be equal plus minus L0 times square root of 1 plus omega squared 0 t squared. You see, that's the result. This is our function. But between two signs, which one do we take? Exactly, we take the plus sign. We'll have the plus sign. So as a function of time, we now recovered x of t is equal to, look at this. This is the result that we were driving for. Now we have the explicit expression for the coordinate of the sliding bead at any moment of time after the thread was cut. The whole thing rotates with variable angular velocity. We will recover it in a few seconds. But now that we have this expression over here, when does t becomes the time of interest, the separation time? When x becomes L. So now we put L over here. X equals L equal to L0 times square root of 1 plus omega 0 squared t separation time squared. And now all we have to do is solve this equation for the separation t separation. And in this specific form, the material that I was discussing a few seconds ago in terms of the arc function or inverse functions become explicitly obvious here. We want to solve this equation for the variable t and thus construct a function that is the inverse of our function x of t. And in real analysis, we have all sorts of wonderful theorems that state when that is possible. But in this case, this is nothing but the good old middle school algebra. And if there's one thing I learned while writing on Quora over the years that I was writing on Quora is that when you write for global audience, you cannot make any assumptions. So here, of course, most of our viewers should be able to swing this right away, but just to make sure that we're all on the same page, everything is explicit in public setting, there are no secrets. We show how we unfold this equation over here. We'll divide this equation through by L0. L divided by L0 is equal to square root of 1 plus omega 0 squared times t squared. Now we square both sides of this equality and we will erase the square root over here. So here it will be L squared. And now we take 1 from the right hand side and move it to the left hand side. This transition happens to be with the negative sign. This is equal to this. And now we divide both sides of this equality through by non-zero real number, omega 0 squared. So from here, it follows that we can already write down the separation time. T separation is equal to, again, because the time is squared, when we technically take the square root of both sides, this square root can be with the plus sign, with the minus sign. This is the forward flow of causality. The time flows forward, so we take the plus sign. Now here we have 1 over omega 0 times square root of L squared divided by L0 squared minus 1. Again, look at the interesting situation where, again, mathematics works unreasonably well with the reality. Don't forget that in theoretical physics, everything that we do is what is a model. Just like the way we construct differential equations to model the real life phenomenon, in mathematics we create a mathematical model of a given physical phenomenon. So everything is a model. And in this model we have, again, look at this, L is strictly greater than L0. It means that L over L0 is strictly larger than 1. The square of this quantity is even more larger than 1. Consequently, from the way more than larger than one number, we subtract 1. This number remains strictly positive over the field of real numbers. That is the only square roots that we're allowed to extract of non-negative quantities. And here is the quantity strictly non-negative. Everything seems to be correct. Remember my remark about hard scientists. Every true and genuine hard scientist is always, no matter what, in the middle of the night, after a wild party on Saturday morning, still skeptical. So we think that mathematically at first blush things look reasonable. This is our separation time. We have our result, and now that we have this result, we can answer the following question. What is the shape of the velocity, not as a function of coordinate x, but as a function of time, v, as a function of time? And after that, we will compute the angular velocity of the whole system as a function of time. And in order to construct v as a function of time t, we have option. The first option, we have options. The first option would be to take the expression x of t and simply slug it into this formula, where we developed a relationship between the velocity and the coordinate of the sliding bead x, but that feels like quite a bit of work, and to some extent it is probably a good idea to carry out this computation by hand at least once to see what it takes. That's one option. The option number 2 is simply to use the definition of the velocity as the first time derivative of coordinate dx over dt, and we can readily write down the expression for that derivative. What it will be the square root taken into the denominator, and in the numerator we'll have omega squared 0 times 2t. This is t squared 2t, and 2 in the numerator and 2 in the denominator will cancel out, and we will have the following. L0 times, let's write down here like so, omega 0 squared times t divided by square root of 1 plus omega 0 squared t squared. This is our result for the velocity of the sliding bead with respect to the rod. This is our expression. And now let's say again we move away from this specific problem. We step more into kinematics, which is not really clear what is it. Is a particular branch of physics, is a particular branch of mathematics, what is going on here. But let's compute the value of the following limit. The value of the limit when time grows without bound, t tends to positive infinity, of v of t, like so. This will be the limit when t grows without bound of the following expression. L0 omega 0 squared times t divided by square root 1 plus omega squared 0 t squared. What is this limit? All sorts of wonderful real analysis theorems. The limit of a product is the product of the limits, provided that the limits exist. Here we have the constant carried out, and here we have t in the numerator and square root of 1 plus this wonderful expression t squared. Well, when t grows without bound, we can throw out 1. Square root of omega squared 0 times t squared becomes what? Omega 0 t. T in the denominator and t in the numerator cancel each other out, and we have the following expression. L0 omega squared 0 divided by omega 0. Don't forget, when we throw out 1, take the square root of this expression, omega 0 still percolates into the denominator. T becomes t, instead of t squared, t1. T and t cancel out. This is what we have. Bam, bam, and this is our result. L0 omega 0. It means that in the limit, when the system becomes kinematic and instead of a finite line segment, we have an infinite ray rotating in the horizontal plane, the way we explained. If the angular velocity, which we're about to compute in a few seconds, decreases over time, asymptotically the velocity of the moving point tends to a finite value, which is this one. Again, the dimension analysis tells us that this seems right. the length is measured in the units of distance. The angular velocity is 1 over some unit of time. So we have distance over time gives us velocity. This is precisely the case, and this is an interesting situation where, again, asymptotically, if the system is allowed to run for as long as we have patience to, then the velocity of the sliding bead will tend to stabilize at a particular value. And if you graph this function over here as a function of time, then it will look something like so. I already did it myself. I recommend that you guys do it yourself too. So this is perpendicular, this is t, this is v of t, this is 0. So this function will behave, the partial graph of this function will behave as follows, like this. There will be some interesting change like this, but then again, asymptotically over long periods of time, this value right here will be precisely L0 omega 0, and the velocity of the bead as it slides over the infinite ray that rotates with a slowing down angular velocity will tend to stabilize and approach asymptotically this here number. And now that we're done with the angular velocity, let's write down the expression for the now that we're done with the linear velocity of the bead relative to the rod, let's do the same for the angular velocity, omega as a function of time. And as a final step, I pre-wrote the expression for you over here for the square of the angular velocity of our system, which I took from where? Which I took from this here expression. Remember, we have v squared in the numerator and x squared in the denominator. And we now know the portraits of all these two functions, x and v, as the functions of time, x of t, v of t. So here we have the following result. The expression for the v squared, this term or this material squared, L0 squared times omega 0 to the 4th power. Remember, 2 times 2 is 4, t squared over square root squared evaporates, so we have this guy over here, and in the denominator, what do we have? We have x squared, this expression squared, L0 squared times 1 plus omega 0 squared times t squared. And what do we see? Well, look at this. L0 squared, L0 squared, L0 squared uniformly cancels out, evaporates. We have only omega 0 squared here in the numerator. Once we move the top of this fraction to one denominator, we'll have omega 0 squared, and then we will have omega to the 4th power, see, squared times squared, 4th power 0, t squared. So these terms times this cancels out, only omega 0 survives, and this denominator goes over here and becomes what? This guy squared. So we will have here the following result. We will have omega squared 0 in the numerator and 1 plus omega 0 squared t squared also squared in the denominator. See, this times this becomes square. Everything is fine, some cancellations, and boom, voila. Now we take the square here and the square here, extract the square root from both sides, take the positives, take the plus sign, and here is our result. Omega of t is equal to omega 0 times 1 over 1 plus omega squared 0 t squared. This is the result for the behavior of the angular velocity when there is no external input, and whatever energy was given into the system, however this mechanism rotates this fixed vertical axis to which there is a rigid connection of our rod. So whatever juice the system had at the beginning, that's the juice goes into that's the juice that goes into the system. But as the point mass slides away from the fixed vertical axis of rotation, it becomes more and more difficult. The effort to rotate the distant mass, the mass that is more and more distant from the axis of rotation, becomes more and more increasing. More effort is needed. This effort is not there. Boom. the angular velocity of our system decreases with time over here, like so. And what do we see? If the system is left to its own devices to run as long as we want to, as we have patience to, in the limit when time grows without bound, then the limit of our angular velocity becomes what? It becomes 0. The system will tend to slow down, which again makes sense. This is basically a mathematical confirmation of our physics intuition that when the system rotates in such a way that there is no external input, eventually over long periods of time it will tend to stop rotating, because the system will not possess enough, let's say, torque or enough rotational juice, so to speak in plain English, to swing the whole thing and keep it rotating in the horizontal plane. But now let's do one final sanity check. Remember, a true hard scientist, especially theoretical physicist, is always skeptical, because in the words of Albert Einstein, the universe never ever gives the theoretical physicist a resounding yes. It's always a very flimsy, very meek, and very not willing maybe. So now the sanity check. When time is 0, time t equals 0, what do we have? When time t is 0, 0 times any non-zero real number is 0. 0 plus 1 is 1, square root of 1 is 1. So we have x of t equals 0 is equal to L0. Is this the case? Yes, it is the case. Look at here. In the initial steady state, our point mass, our bead, sits at the distance L0 from the origin of our coordinate system. Now, what about the velocity? V when t is equal to 0. What's going on with the velocity? Well, let's go back to the tape. Ladies and gentlemen, when t is equal to 0, 0, 0, 1 plus 0 is 1, square root of 1 is 1. What is this? 0. The whole thing vanishes. So no initial velocity of the bead with respect to the rod. Again, makes sense. Things converge. What about the angular velocity? Angular velocity when the time is 0 becomes what? Let's take a look. 0 times non-zero real number is 0. 1 plus 0 is 1. Anything divided by 1 is whatever that anything was, omega 0. And this is precisely the case. This is the set of initial conditions in our system. So this seems to make sense. We feel good about ourselves. Chances are that we have solved this problem correctly. Now, this is it for the physics problem S3E39, and we will move on to a new challenge next. Our next challenge will be a problem in computer science. It will be the problem number 9 for the season number 3, S3CS9. And this will be a wonderful little puzzle. And in general, this will be a problem that you either like or do not like. This is how these things work. But I personally like these problems because for these problems, there exists a miniature cottage industry, which is somewhat narrow but quite deep, because in this universe of computer science / mathematics, there exists a bewildering array of problems that are formulated in your native tongue, whatever it is. English, French, German, Dutch, it doesn't really matter. Spoken English, no technical jargon whatsoever, no group isomorphisms, no kernels of group homomorphisms, none of this highbrow mathematics. Plain, daily spoken language, spoken tongue. However, behind that innocent sounding and innocent looking plain everyday spoken language, there sits usually a pretty deep mathematics and maybe a little bit of physics and definitely computer science. So here is the problem in computer science, and that alone is a hint. The setup of this problem may seem a little bit contrived, a little bit elaborate, but this is a completely legitimate problem, tested, and the solution is quite wonderful. It admits several solutions. I will share my solution with you in the next episode, but the deal here is the following. We're given 8 boxes, visually indistinguishable, identical no matter how you look at it. One diamond. Oh yes, one diamond. And 2 people, 2 lucky contestants. The objective for this problem is the following. The rules of this game that the two contestants play is the following. These 8 identical boxes, visually indistinguishable, are arranged in a random configuration in such a way that when one person, the first person, is walked into the room is not transparent, nothing can be seen through, isolated, the whole caboodle, pedantically completely isolated room, and in that room with a random configuration, these 8 visually indistinguishable boxes are arranged either facing the first person who's walked in, the long side or the short side over here. This is just a sample configuration. That configuration of long and short sides is completely random. It could be anything. You cannot know with certainty what that configuration of long and short sides will be until you, as a first person, as a first contestant, are walked into the room. Somewhere in this 8 boxes there's one diamond. It's also hidden, and you will be shown as a first person, you will be shown which box the diamond is in. What you're allowed to do is you're allowed to perform some manipulation with these boxes. You have to leave them pretty much the same, but you can change only the configuration. You can change the long side or the short side that faces the second person who will be walked into the room, but this is the only thing you can do. There are no other forms of communication. This is how the problem is set up, and the setup leads to a clean computer science solution. And my solution will be revolving actually around a little bit the theory of groups and some basic computer science. So once the first person is led into the room, that person witnesses the random configuration of long and short sides of 8 visually indistinguishable boxes. That person is shown that the diamond is in the box blah, for example. Let's say the diamond is in the box 6. Then that first person has to do something to the configuration of these boxes, and then that person is escorted out of the room. Then once the first person has left the room, the second person, the second player, comes into the room, and that person is already not told where the diamond is. That person has to somehow discover correctly, with absolute certainty, which box the diamond is in. And according to the rules of the game, these 2 people, the 2 contestants in this game, of which one person, obviously the first person, will know where the diamond is, but after the first person is taken out of the room, that person will not have any contact with the second person. No radio, no internet, no nothing, no iPhones, no Morse code, no smoke signals, no nothing. All of this fancy problem-solving techniques or lateral thinking are out of the box, so to speak, are out of the rules. The only thing that the second person can do is somehow agree with the first person on the strategy, of what will be done to these boxes, so that once the second person walks into the room, that person will look at the configuration of the boxes, do something, some computer science, some mathematics, and then say, with absolute certainty, the diamond is in the box number blah. And if that's the case, then the 2 people get to keep the diamond, and if not, then no diamond for you, no cigar. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the computer science problem, S3CS9.